Hello and welcome back to my channel. In today's video, I'm going through Class D speaker amplifiers. I'm going to be using the Max 9768 port for this. This is a 10 watts mono amplifier, so we'll be using two of these chips for two speakers. If you remember from the last video, we tried to design a Class AB amplifier. I'm still working on that circuit and there'll be a video coming up on that soon. In this video, we will be doing the hardware design for Max 9768 with the surrounding components that we need. So first of all, I'll show you how to set up the schematic, some of the important parameters on the bill of materials, and then we'll go to the PCB design. I would like to extend a huge thank you to NextPCB for sponsoring this video. I have gotten boards manufactured from them in the past and they have been excellent quality. From prototype to production, NextPCB offer very good quality and service, from PCB manufacture and assembly as well as component sourcing, all tailored to your needs with a very quick turnaround time. They also offer a DFM tool on their website, which was very useful to me when I was designing my power electronics board with the switching regulators. They highlighted many issues that I would have during production, which I then fixed in KiCad and was able to get the boards manufactured. So again, a huge thank you to NextPCB for sponsoring this video. Max 9768 utilizes Class D topology for audio amplifiers. Obviously, if you want to learn more about Class A, Class AB, Class B, Class D amplifiers, there are a ton of videos on YouTube that you can follow. I'll try to leave a link for some of them in the description below. Class D amplifiers tend to be higher efficiency when compared to Class AB or Class A or Class B. This amplifier offers relatively low distortion and has some integrated features that I think will be useful for me. It's got analog volume control, as you can see on the datasheet right now. It's obviously very low package size. It's got low quiescent current. And there's two modes of operation. For one of the modes, you don't have to utilize a lot of filters on the output side. I am going to try to make the design a little bit flexible so that I can do both modes. Obviously, I don't want to have a microcontroller or anything like that on this design, so I don't want to use the I2C volume control. But what I will do is add in some connection points that if I wanted to add in a microcontroller, I can do so. The amplifier itself can operate from 4.5 volts to 14 volt supply and comes in a very small package, which might be a downside because obviously I'm testing. Now, to kind of give you a background on why I'm doing this, obviously this is for me to learn about Class D amplifiers, how they work, and hopefully get something working. I've never done anything like this before, so there will be a bit of a learning experience for me. I follow good design practices. If you have any recommendations for me, please let me know in the comment section below. I'm hoping by the end of this we have a working Class D amplifier and we learn something. That's the main aim here. So let's get started. So first of all, what we will do is make a KiCad project. I'm using KiCad 8 for this. So in order to do that, you need to go to File, New Project, and save it in the location where you normally keep your KiCad projects. In my case, obviously, I'm keeping it in audio amplifier example. So now I've got the project created. Obviously, you can see I have two files over here. One is the schematic and the other one is the PCB. To open the schematic editor, you basically press this button over here, which brings you to this page. The first thing I would do is set up the page. So obviously you've got your issue date, you've got your revision. So this is rev dash or the first revision. So basically there have been no iterations on this design. The title, I'm going to call it audio amplifier example. And I'm going to make this size A3 so that the board doesn't become too crowded. So you can see all the details are filled in over here. Obviously you can add in more details if you need. So for the amplifier itself, I'm going to be trying to follow as much as possible to the recommended typical application circuit, which is shown on over here with the analog volume control. Obviously the design is quite simple, but some of the things that we need on this are regulators for the power supplies. So you can see we've got two power supplies on this component. We have a high power supply here, and then we have the digital power supply for the low level logic in here. So the typical range for that obviously is 2.7 volts to 3.6 volts. I don't expect there'll be much current going through this path, but we can have a look at how much current will be going down or how much power will be required for this node over here in the datasheet. The second power supply over here is the high powered power supply, and this can go up to 14 volts. So 12 volts is quite common in terms of power supply and regulators and things like that. So that's what I'll be using. And I want to, for this design, go for LDOs as they tend to be low noise, and that might be slightly better suited to this. Obviously that means that they're going to be less efficient compared to switch mode power supplies, but as a first go I think that'll be fine. And then we can change out the power supplies if we need to see what effect it has on the noise levels. We have some filtering capacitors on this. We have a boot capacitor that connects from the positive and the negative output to the respective boot minus and positive pins. We have a high pass RC filter on this and some feedback resistance over here. There is a control to mute. Obviously, if we go to 0 volume on this potential divider, then we don't need to mute. So I will be basically connecting this node to ground, and you can see from this schematic over here, you mute input. If you drive this input high, then you mute the speakers. Obviously, if you wanted to make the design more flexible, then you can add in some nodes there in order to like add a switch or something like that. The sync pin in the typical application circuit is connected to VDD, which is this pin over here. So that's connected to a voltage, a relatively low power voltage line. And what that does is that it lets you select the frequency and gives you an external clock input. So obviously in the typical application circuit, it's connected to ground. That means the switching frequency inside the max 976A is going to be locked at 300 kilohertz. If you leave it unconnected, you can up that switching frequency. And you also have this mode where you connect the pin to VDD, which is what we are doing. And in this mode, what it does is that it spreads the switching frequency around the 300K mark and modulates it up and down by 7.5 kilohertz. And this reduces the power at certain frequencies and makes it easier to pass EMI requirements. So obviously in the typical application circuit, this is the mode that we're using, and I'm going to stick with it as I understand more about how this chip and Class D amplifiers work. So I want to keep it relatively simple, but we can do other modes if we need to. We can change the operating frequency of this component by having a clock input over here. So whether that's coming from a microcontroller or something like that, and then you can select your own operating frequency. Obviously there'll be some maximum limits on that as well. You have the bias pin over here with a 2.2 microfarad capacitor connected to the pin. The only pin we haven't spoke about is the sync out. And just let's quickly have a look at what that pin is doing. So you can see in this application, it's the clock signal output. So I think the use case for sync out is when you're trying to drive two mono Class D amplifiers. So obviously if you've got two max 9768s to drive two speakers, you want them to sync up so you can transport or translate one of the clock signals to the other one. Obviously we'll need to be a little bit careful here because 300 kilohertz is not the highest of frequencies, but it could potentially have high ramp rates. So maybe we need some termination resistors and things like that on this line. As I'm doing two of these in parallel to drive two speakers, I will need to connect the sync out of one of them to the frequency input of the other one. So first of all, let's bring in our main component. The component doesn't exist on KiCad, so I'll have to create it. In order to create a new symbol, you need to go back to symbol editor. And then basically you can use one of your existing libraries. For example, we created my library before. You can right click and press new symbol. The name of this symbol obviously is max 9768, and then press the OK button. So I'm just going to move this out the way. And what I'm going to try to do is basically just replicate what they've shown over here. There's quite a few pins over here, which I might change the layout. I might not, but we'll see how it works out. We can always adapt the symbol later on if we need to. So to place a pin, you can either press the P button or you can click this symbol over here. So pin number 1 I'm going to put down is basically pin number 1 from this symbol over here. And you can see from this schematic that this pin is an output pin. So I want to label this pin as an output pin. And this helps with error checking, which you can set up in KiCad. So let me put that down here somewhere. And then obviously there's another pin that is the same connection as that. So the name of this pin is out plus, the pin number is pin 2. And again, it's an output pin. I need to change the name of this pin to out plus as well. So now I'll basically do all the pins for this pot, and I'll see you after I've done the pot. So obviously this part has a lot of pins, and to kind of look at the pin table, you can press this button over here to open the pin table, and that should give you all the pins that you have put down on this symbol. So obviously we want to make sure that we have all the pins accounted for. So obviously in this case we have 24 pins on this part, and we have 1 2 3 4 5 all the way up to 24, and we're not missing any pins. Next, I'm going to check that I've got all the pins labeled properly. So this is not a power input, this is just an input, and I think I have basically got all the pins covered. So you can see I was arranging them before, and I felt that the layout that was on the schematic itself is quite messy. So what I'm going to do is come up with another layout for this part. Hopefully that makes it a little bit easier to read, but we'll see. So for me, I always prefer the power supplies to be on the top. I have my communication channels on the side over here. And obviously I need to rotate this. Then my output I want on this side, and I'll bring it all in together afterwards. So this is my negative output. Finally, I want to put down the square box to kind of bring it all together. Background color over here, which will give you the standard color that KiCad uses. This is your reference designator. I'm going to put it on that top corner there. And then finally add in some text to show. You can see now the part is nicely centered. What I'm going to do is save this part. Another thing I didn't mention was selecting the type of electrical connection this is. And this is used for error checking on the schematic. So obviously if you connect a power input to another power input pin, the KiCad software can flag up that you've got two power inputs connected together, which obviously doesn't make sense. Because obviously you would want to connect a power output to a power input, or if you have an input connected to an input, that wouldn't make sense as well. So then it can flag up some errors like that. So press the save button, close this, and go back to my schematic. So now if I go and try to use basically max 9768, you can see now it exists in my library, and I can put this part down. So that is the symbol I just created for this part. Finally, I'm just going to draw the circuit or the components required around this. I have already gone and made a bill of materials that I'll be needing. Obviously, I'm going to get this board manufactured at a later date as well. So I've got the max 9768, and I've got a bunch of other parts that I need, mainly capacitors, a few resistors, and audio inputs, outputs, things like that. So let's now put these parts down. So firstly, I want to have a barrel jack, and the input voltage on this is going to be approximately 15 volts, I think. So I'll just put in a pad to show that. Next, I want to have some good decoupling on this and a large value capacitor to smooth out the power supply and help with filtering. Some large value capacitor will be enough. I'm going to go for 22 microfarads over here. And this is decoupling for the board. Obviously, I'm going to have separate decoupling capacitors for the power pins over here. Non-polarized components. It's always a good idea to add in some net labels. So obviously this is 15 volts. So I'm going to add in V15. This will go to a regulator, which I will add in at a later time. You can see this is VDD, so that's going to be 3 volts over here. So we should have a power symbol for that. So 3.3 volts DC. I'm also going to add in a track here. These are going to be 12 volts DC. I'm going to change that to just 12 volts because to keep it in line with this. The reason why I've not added 3.3 volts is sometimes it's difficult to read the dot when you print out this. Because what some people will do, or what I would likely do, is print this out in A4. And obviously this is an A3 sheet, which might get rid of some detail on this and make it difficult to read. So we need the 2 boot capacitors over here. And they go back to pin 17, 18. Just to make it easier to read for schematic, I'm just going to add in all the net labels wherever I can, or wherever they make sense. So net label, boot plus, and that goes over here. I can make the size of that a little bit smaller. Copy that and put that down here. Obviously that, make sure to change that to boot minus. And just move it up a bit so that it's not right on the pin. The regulator I'm using is AMS1117-3.3 for the 3v3 regulator. And I also have a 12 volt regulator, which I don't seem to have a symbol for in this. So I'll need to make that symbol as well at some point. So let's quickly have a look at the datasheet for this part. Obviously, this is just a cheap part that I'm using, but you can see you've got pins 1, 2, and 3. I'll make sure that lines up. So pin 1 is ground, pin 3 is the input, and pin 2 is the output. So the input to this part is going to be 15 volts. So I can move this up here if I want to. I think I'm gonna prefer to keep it down here because I know I've got other regulators on the board as well. So I'll put that down there, and then I'll just look at some recommendations for the input and output capacitors from this datasheet over here. So we don't have the adjustable version over here, obviously. We've got this one, and the recommended capacitors, it looks like, is 10 microfarads for the input and 10 microfarads for the output. I'll see if there's any more information on those values anywhere else. Now it seems to be just that information there, so let me grab these capacitors from here and put them down. Obviously, what that is the 3v3 output, so I'm going to put that node over here. You can see, because it's a linear regulator, it's very simple to put together. And with these two 10 microfarad capacitors, it should just be fine. Obviously, this outputs a lot of current, 1 amp. I don't think we'll need it that high, just for the VDD line. But I want to keep this package because I have some of these components already. You can see the current that's going to be supplied to this is 14.2 maximum milliamps, but that is when it's not doing anything. We need to find the normal current that goes into the part. So on this figure over here, it shows you how much supply current you need on the VDD line and against the supply voltage. So obviously we're doing 3.3 volts, which is around here. So this will only need around 10 milliamps. So I'll just make sure that the regulator is not going to be unstable at such low currents, which I don't think it will be for LDO. The regulator itself will take a significant amount of that. However, I'm not particularly worried about power consumption on this board. I just want to focus on low noise for now. In the typical application circuit, we have a feedback resistor of 30 kilo ohms. So I'm just going to put that down over here. And that is connected between the input pin and this pin over here. So again, adding my net labels in, just going to call this feedback. And then we have a low pass filter on this side, and that has a value of 470 nanofarads, and the resistance value is 20 kilo ohms. So this is our audio input over here, and this node is going to be audio in but filtered. Next, I want to connect up the grounds. So put down my audio connector over here. It's slightly out of place. I mean, I would normally put my inputs right on this edge over here, but I don't think I'll need that space. So this audio connector over here, you have T, R, and S. The T stands for tip, which is going to be one of my channels. The R is going to be another channel, and the S is sleeve, which I believe is going to be on the ground. I will double check these connections on my instrument to make sure I've got them correct. So I'm just going to call this audio in R. Audio in R filtered. And I don't need that unnecessary crossover, so I'll just basically connect this up here. Let's quickly discuss the input connections to this audio amplifier. So obviously we have a 470 nanofarad capacitor, we have a input resistance of 20 kilo ohms, and we have a feedback resistance of 30 kilo ohms. So looking at the data sheet, there is an internal operational amplifier over here, and this feedback resistance along with the input resistance will set the gain. So just quickly looking at the calculation for the gain, we can scroll down to the adjustable gain section where we have this equation over here, which describes the gain is equal to -10 RF over RN. There is also an internal gain, however the maximum gain is decided by this. There is a recommendation from the data sheet to choose a value that's between 10 kilo ohms and 50 kilo ohms. So obviously you can see on the schematic that we have, we have gone for 30 kilo ohms, which sits right in the middle. What I might do over here is add a secondary through-hole resistor and make that a do not fit resistor value. So just in case I need to change the gain feedback, I can basically adjust this resistor value up and down if needed. And just a little note so I remember why I've put this resistor over here. Now finally, let's talk about these two components. So we have C9 and R2, which form a high pass filter. They do two things. They remove the DC voltage from this line over here. So if there is any DC offset on this line, that will be removed. And they remove frequencies below the cutoff frequency of this. The 3 dB point for this filter can be calculated with the equation given in the datasheet just over here. So that's the input filter. An input capacitor in conjunction with the input resistor forms a high pass filter, as I described it before. And basically this is to AC couple it and also to remove very low frequencies. So the equation for that is given, so the cutoff frequency for that filter is given by this equation over here. So we have a 20 kilo ohm resistor and a 0.47 microfarad capacitor. So to calculate the cutoff frequency, so F3 dB, it's equal to 1 over 2 times pi times Rin times C. So that gives us a cutoff frequency of 16 Hertz. So well below the 20 Hertz audible range. Obviously there will be some attenuation at 20 Hertz. However, if you look at most audio signals, we're not going to be playing in those sorts of ranges anyway. This will compromise the signal a little bit. So if we wanted to, we can adjust this filter down by increasing the value of this capacitor. So let's say I move this capacitor up to 1 microfarad. The cutoff frequency is gone down to approximately 8 Hertz. So either I can follow the recommended datasheet number, or I can basically go with a 1 microfarad capacitor on this line. Some important things to note on this capacitor value here is it's a good idea to have or to use a tantalum capacitor or a electrolytic capacitor in this application. Using a ceramic capacitor here can induce a distortion on the audio signal as the capacitance is dependent on the voltage. I can recommend reading this application note from Newark, which compares the voltage coefficients of capacitors. So that basically describes how the capacitors are affected by large DC voltages. Now you can see over here that ceramic capacitors have a large voltage coefficient, whereas film or aluminium electrolytic capacitors or tantalum capacitors are a lot better. I'm going to go with a aluminium capacitor in this case. This graph describes how the capacitance changes with DC voltages. So you can see as the DC voltage is increasing, on this capacitor, the effective capacitance value is going down. And this is for an X5R dielectric. Now, if I was to use an aluminium capacitor, you can see the capacitance change with DC voltage is very low compared to the ceramic capacitors. So in order to achieve that, I'm basically going to add a note in here and change this capacitor to a electrolytic one. I'm also going to go for a 1 microfarad capacitor. And obviously if I need to change that around, I will do. But then that gives me a 3 dB cutoff point of 8 Hertz approximately. And I can leave that as a note on here. So these notes will help to choose the bill of materials or components. And if someone looks at this circuit in the future, then they know what's going on and why these values were selected. Now to get some flexibility from this chip, basically the MAX 9768, I'm going to connect up these with some solder pads and everything so I can change around the connections quite easily. So let's just look at the mute pin first. The mute pin can be connected to the 3v3 line, and that basically mutes this connection over here. So if the mute connection is driven high, obviously that turns off this connection over here. So I will obviously need a bit more space. So what I'm going to do is use net labels, and hopefully that makes it a little bit easier to read. So I'll bring that out over here. I will put in some pull down resistor to keep that down low. So this board will just basically be not muted when this is not connected. And then when if I want to change that, then I can basically connect something to this pin over here and connect that up to 3v3 to enable the mute function. That is a little bit crowded, so I'm not entirely happy with that, so I'm just going to move that out the way. The bias pin is very simple. I just need a 2.2 microfarad capacitor in there. I think this pin might be best to move it out the way so that it's not in any of these functions way, and potentially over here or down here. So I've made the changes, and now I need to update this schematic. You can see my pin has now moved down here, and I need a 2.2 microfarad capacitor. So this 2.2 microfarad is a recommended value from the datasheet. For the output filtering, which goes to the speakers, there are two options basically that we can select as the operating mode for this audio amplifier. The standard or the default mode is a filterless class D operation, which is described on page 17. So if you have very short leads to the speakers, you can basically have no filtering on the output. The main reason for the filtering is to help with EMI and EMC radiation limits. So basically, if you are going to sell this product into the market, the EMI emissions from this product needs to be less than a certain value. And this product can meet those limits if the speaker length is shorter than 10 centimeters. However, obviously I'm on a long lead speakers. So what I'm going to do is add a ferrite bead on the output and a capacitor value. The capacitor value is dependent on how long the leads are. So it's going to be a little bit of trial and error because some of my speaker lengths are different anyway. But I'm going to aim for a ferrite bead with impedance of approximately 100, which is rated to at least 1.5 amps as recommended from the datasheet. And for the capacitance, I am going to use 330 picofarads, which has also been recommended from the datasheet. Obviously that forms a low pass filter, which we can calculate the cutoff frequency for. However, that's going to be well above the 20 kilohertz, which is the audible range. So let's now draw the output filter. So I'm going to put down some ferrite beads and a capacitor to ground. The value of these capacitors is 330 picofarads. Another thing I'm going to do is add in some extra filtering on this, but I'm going to leave it as no fit, and then I can fit in those components if I need to at a later date. So this is a filter between the positive side and the negative side that's driving a speaker, creates a low impedance path for high frequency noise that is present. Finally, this will then go onto a speaker. So I'm going to see if I can find any RCA sockets on this. So I'm basically going to use this. So this is my output socket, which will go to the speaker. For the shutdown pin, I'll do something similar to what I've done for the mute. So in this case, I need to have the shutdown pin connected to 3v3 all the time. And then if I want to use the shutdown function, I'll basically need to connect it to ground. So I'm just going to use the same setup that I've done for this one over here. So I'll bring this out. Connect it to 3v3 with a pull-up resistor. And then have the possibility of connecting that to ground as well. So the pull-up resistor will keep this normally at 3v3. So that will make sure that this amplifier stays on. And then if I need to use that functionality, I can basically connect something between these two nodes. I don't really need the secondary node here, but this just gives me a bit more flexibility. So SCLK needs to be connected to ground for filterless mode, which is what I'm going to be using. So what I'll do is add a jumper pad that lets me connect it to ground easily, and then I will add in a pull-up resistor value as well. So if I need to connect this to a I2C line ever, what I can do is basically connect this up to a external pin. So I'll add that pin in now. It's a good idea to keep the connections separated like this and not have a four-way bridge. So sometimes it's hard to tell if all the connections are connected. So if they're separated like this, you can make sure that all connections are made. And then if you print it out as well, it's easier to see. So I'm just going to add a little note here for future reference. Now, if I don't have a microcontroller, basically the volume needs to be controlled with a variable resistor, which would connect to this pin over here. So I'm going to bring this pin out. Similar to what I've done over here, I need to connect one node to 10 kilo ohms resistor. And that's if I'm going to be using a microcontroller to ever control the volume on this, or I connect that to a variable resistor. So that will require a three-way jumper pad. So connecting pins 2 and 3 lets you put the 10k pull-up resistor required for I2C communication. Connecting 2 and 1, I need to basically send that connection off to a variable resistor, which will do analog volume control. Now these things can generate a bit of noise. It might be a good idea to add a small capacitor on this line to filter out that noise. So to do that, what I'm going to do is add a 10 nanofarad capacitor. Finally, I'm going to add in all the net labels. Another thing I've missed out from this is the pin connection for the I2C communication. So obviously if I were going to use the I2C channels, then I need to connect to the data line and the clock line, which is on these two pins here. So I need to keep those two connections together on the PCB design. So I'll make a note of that over here. The last two connections that I need to make are ADDR2 and ADDR1. Something I need to keep in mind is if I'm going to have two of these audio amplifiers, I'll need to set different addresses on them. So what I will do is provide that flexibility to change the addresses on them as I need. So I'm going to do that using these jumper nodes. So we can either connect that to digital high or the ground to set the different addresses. So I'm just going to have the option of doing both. There are quite a few jumpers on this board, but this is basically to keep the flexibility for a development board. The last thing I'm going to do is add in a connection point for this. However, I don't think I will ever use it. I can move all of this to the right and then basically gives me a bit more space to add in a net label over here. So let's now quickly sort out the ground connection. So what I need is a star node first of all, which hopefully I can find on here somewhere. I don't think there is a star connection. So what I'm going to do is just use a 3-pin jumper pad, basically connect that up to this node over here. One of my nodes on this line is going to be the normal ground. And then the other one will be the power ground, which I need to get a symbol for. So I need a ground digital and I need a ground power. So I don't really like that symbol. I'm just going to use this one for the power, so and make sure to change everything. So the ground digital, basically that's anything that's connected to the 3v3 line. This regulator, that's this junction over here. And all of these functions, they're all digital functions. The intention of this is so that I have a final connection or a single ground connection point very close to the internal supply or the incoming supply. The only pin I need to check is the bias. I think that's for the analog side, so I think that's going to be connect up this pin to ground. I think it's for the analog input side. So it's going to be running off the 3v3 line, I think, and not the power line. So the last thing I need to do is basically the regulator for the 12 volts, which is going down over here. I have also added in some directives which tell me what this is. So what I'm going to do is rename that to 1 amp. And this will help to remind me that there is a lot of current going down this path. I'm going to basically put those nodes on here as well. The SDA and S clock line can be high frequency, so I might just put down high speed, just as a reminder that I might configure that as high speed at some later date. I'm now used to doing the directives in Altium. I'm not entirely sure where I can set some rules on here. I'll figure that out and I'll get back to you. I'm going to add in some pin connections on this as well, and this is just for testing purposes only, so it's easy for me to apply a bench power supply to this node. And I should add in the high current directive on this as well as a reminder. So let's now create the 12 volt regulator, as that part didn't exist. So looking at my bill of materials, which I created a little while back, it's basically this part here, and I need 2 of them to power the individual audio amplifiers. So let's go to the symbol editor and create the 12 volt regulator. So as before, I'm going to use my library and add in a new symbol. The port number for this is CJ7812, and it's a port that I already have, so that's fine. And obviously this is a linear regulator, so it's going to be relatively simple with 3 pins. So pin number 1 is V in. Pin number 2 is ground, and pin number 3 is V out, so that's pin 3, and that's power output. And then finally, I'm just going to add a box around it. And some text to show the port number, so we CJ7812 12 volt reg, and save that. So I'll be able to use this now on the schematic. But this regulator doesn't need high capacitance on the input lines. However, I'm just going to use 10 microfarads to reduce the number of BOM items. So 15 volts coming in, and it's going to be 12 volts going out. And obviously this is going to be high current as well, so I'll delete this. I don't need this connection over here, it's already on this line. Don't need this one there. And I need to connect up this to the power ground, which is this one. I do need 2 of them for the 2 audio amps. Now I'm unsure how well 2 of these will fit on this. So finally, I think I have completed my schematic. So you can see I have a audio input jack over here with the sleeve connected to ground, the right input on the ring and the left input on the tip. I've connected the clock and the data lines for the I2C together for both chips, so eventually if I do add in a microcontroller, I can do that. Obviously I've got the jumper pads for the addresses if and when I need to change them. Finally, I've renamed some of the net labels. so that the circuit is clear in which side is the right output and which side is the left output. So you've got the right output on the top and you've got the left input on the bottom. There's less circuit on the bottom one because there are a few components it's sharing from this end over here. The output filter looks exactly the same on the left hand side, and then obviously the decoupling capacitors also look the same. I have two individual 12 volt regulators that power the left input and the right input over here. The 3v3 line is done with this. The 3v3 regulator is powering both the left and the right audio amplifiers, and that's because they're not very high power lines. The 3v3 is only going to take about 17-18 milliamps, if I remember correctly from the datasheet. So that is basically all my schematic done. What I need to do now is go into the footprint assignment tool, which is this button over here, and assign footprints for all the different components that I have. So all 10 microfarad capacitors are 1206. C9 and C10 are the electrolytic capacitors, so I need to be a little bit careful. For the two electrolytic capacitors, I'm using this one here, which is a D4 with the length as 5.3. So I'm going to go with this one over here, and so that's both of those done. All my resistors are 0402. One of the things that I've missed on this component is the ground pad for the power, which from the datasheet says that the exposed pad needs to be connected to ground with multiple wires. So we can do that. It doesn't actually say which one, the power ground or the digital ground. I'm going to assume it's the power ground because of heat dissipation. I have updated the symbol, and I'm going to do the same thing for this one. So double click the symbol, update symbol from library, and you can see the extra component is added here, and I'm going to connect that up to ground. So I have some 24 pin QFN ports here, obviously quite a few options. I need some thermal wires, so that's a given, and then I need to check the size of the exposed pad underneath the component. Unfortunately, the datasheet I have doesn't make that very clear. So these are all the same components here, so I'm going to download one of these. So the pitch is labeled with the notation E. So if you look at small e on here, you've got 24 4x4 and the pitch is 0.5, and the exposed pad size is E2 by D2. So I might need to go back to the package code, which is T2444 plus 4, and the plus isn't important because it's for Roche data, so I'm going to ignore that. And looking at, so this one over here, the exposed pad is 2.6 by 2.6 nominal, and obviously we had the size of the pitch before, so the pad size is 2.6 by 2.6, so that one there. We need thermal wires to ground, so that's over here, that's fine. And we have the one exposed pad with a pitch of 0.5, so this package will do the job. So you can see most of my components are done. The last few components I need to do are the voltage regulators, the potential divider, and the audio input and output. As the final thing for this video, I'm going to show you how to export the bill of materials. And to do that, you need to go to Tools and Generate Bill of Materials. So you can edit what you want to include and what you don't want to include. So I don't want datasheet on mine, for example. I do want the footprint, however, that's going to be wrong, so that's going to change. So I'm going to populate that myself, which you can just tick on this. You can also have do not populate if you want to do that. So obviously there are some bits on here that we don't want the supplier to populate for us. For example, C28. And to do that, basically just tick the group box and it will tick all the components inside there. So where the value is do not fit, I've basically put down do not populate. And that's a very simple bill of materials that I can use. Obviously, if you want it a bit more complicated, you can edit the number of fields and everything like that. You can also get presets, which obviously if you're doing anything a bit more advanced than this, you can use. So that's all I have to share for the schematic today. Thank you for watching, and in the next video I'm going to go through the PCB design for this.